All right, so yeah, my name is Jackson Fender. I did my research in the Environmental Studies department at Elon University. I'm a senior Environmental Studies and Public Policy major, and today I'm going to be talking to you about my research entitled The Light Bulb Tunicate, a study of invasion ecology, climate change, and risk analysis. So thank you all for being here. Just to briefly introduce our team going from left to right, on the most far left, that's Dr. Mike Kingston. He is Elon University Biology and Environmental Studies. To his right is Josh Johnson, who graduated last year. He was one of our GIS assistants and graduated with a GIS minor. Just explain who I am, so I don't need to do that again. And Dr. Amanda Chunko, who is also in the Environmental Science Department, as well as does some work with GIS. So this is our team. Took a lot of people to pull this project together, so very grateful for everybody up there. So at this point, you're probably curious, what is a light bulb tunicate? So the light bulb tunicate is a type of Ascidian species, also commonly known as like a sea squirt, that's native to the Caribbean Sea area. It tends to pop up in tropical habitats, and this is a picture of the inside of one and one fully right here that we took in Beaufort, North Carolina. And as you can see, these are colonial species, so each individual polyp right here is a singular tunicate. And these tunicates are a clone of the original tunicate that formed on the reproductive base that forms the colony. So all of the little tunicates in this cluster right here are essentially clones of one another, so pretty cool. Through GBIF, we have documented occurrences of this species dating back to the late 1800s. So using that data, it gives us an opportunity to kind of see where it started, as we know in the Caribbean, and where it spread over time. And based on that, we've seen that it slowly crept up the eastern seaboard. And this is perhaps due to climate change, perhaps not. That's part of what this study is designed to help further. So we'll talk about that in a little bit as well. And then the basis for our research project was an isolated invasion that occurred in the Beaufort Morehead City area in North Carolina around 2014. We wanted to see if it had spread in the last 10 years, if it had spread outside, how far it had spread, things like that. So our goal for this project, as I just mentioned, was to identify species spread. We want to figure out where it's going, where it has gone. And part of the importance for why that's important is biodiversity. So there are several papers that have come out about this species that claim that this species has a negative impact on biodiversity in communities that it invades. So obviously this is something that if it's spreading, we want to know where it's going and start working to figure out ways that we can contain it in the interest of biodiversity in our local subtidal communities. We also wanted to generate informative maps, which is the GIS part. We want to be able to provide maps to the public that show where the species is, where it's going, as well as potentially in the future different species makeup of the places that we sampled. We also want to make predictions as to why this species is spreading. So as I mentioned before, climate change is often thrown around with invasive species, especially when you're looking at a northward expansion. So we want to figure out if that's actually playing a factor or if there are other things that are more influential. And then we want to predict further distribution and invasion, just so we can allow people in hotspot areas to have an idea of what they should be looking for when they're checking their docks. So this right here is a picture that we took using our sampling equipment underwater. So these right here are the actual species themselves. They look a little bit different underwater. But you can see this is a standing dock piling. The water's a little bit turbid, and we'll actually look at a video of how we got to these in a little bit here, but just to give you an understanding of what it looks like in subtidal communities, what it looks like underwater, this is what it looks like. So compiling our actual data, so we generated a large data set, specifically using GBIF. We had over 722 occurrences prior to the addition of our field data that we generated. That's a substantial number, especially for this species. And eventually, we'll also introduce iNaturalist, which will add over 100 extra data points. So we're looking forward to making that data set larger and more complex. And all of this data has been individually verified by our team. We've gone through the different spreadsheets and verified that they're not duplicate occurrences and that they were actually made in good faith. So that's how we got our museum data that I'll reference later on. So our actual sampling methodology, so our field site selection. So North Carolina has a list of all of their public docks that are available as well as when they're available. So we use those as kind of anchor sites for our supplemental sampling. And we also did supplemental sites based on a convenience sampling technique in between. The goal was to sample every 20 miles along the coast. often that's not exactly possible due to things like military bases and other areas that are inaccessible. So 20 miles was the goal. We stuck as close to that as possible. Not always the case. The criteria for actually making it into our sampling protocol, so the site must reach at least 1 meter of water depth. So this is a subtidal species, so it needs to be able to have some sort of water coverage. So if it wasn't at least a meter deep, couldn't sample there. Salinity reading also needed to be above 15 parts per thousand. So studies have shown that tunicates specifically struggle under 20 parts per thousand of salinity. They can sometimes live in lower salinities down to 8 parts per thousand temporarily, but it's not sustainable long term. So that was kind of our guideline for if it's below the salinity, we can't sample here. And then floating docks, which I'll talk about in a minute, must also meet the salinity requirements while maintaining a submerged state. So obviously when you have standing docks, those are in water continuously. Floating docks can kind of vary depending on where you go, and they can also be resting partially on ground. So it's a little bit different, but most of our data came from standing docks. So 2 sampling devices were built by myself and Dr. Kingston for varying scenarios. So on the top right there, that is our standing dock sampler, which I'll show you a larger photo of in a minute just to kind of get the scale of that. But we built that to lower straight down and capture standing dock pilings. Great video, which it was essentially a garden pruning tool, which we attached a camera mount to for our waterproof camera. And then on the bottom is our floating dock sampler. So this was essentially just PVC pipe, a joint connector, and some super glue that we put together, as well as another waterproof camera mount. And what we would do with that is you can stick it on the side of the sampling dock and then rotate the side with the camera underneath it, and then you can walk around and get the underside where there's still light of the floating docks. Salinity was taken using a handheld refractometer, and all of the coordinates and time of day were recorded at each site in my lab notebook using standard iPhone GPS. So for our camera equipment, we used 2 different cameras for this research. So we used a GoPro Hero Black 7 and then a Akaso Brave LE7. And then we would use these to conduct our actual transects themselves. For the standing docks, we would do up to 10 transects per site. This was spread out as much as possible. Oftentimes there were only 10 pilings that we could actually sample. If there were more, we would spread them out to try and get a better picture of the dock at large. And then floating docks were sampled by area, so essentially as much area as you can get while walking around the 3 sides that are exposed to water. That was what we sampled for those. So this is what I was talking about the standing dock sampling device. So I'm a pretty large person. This is our fully extended research apparatus right there. It clocks in around high 4 to low 5 meters, totally extended. So that's kind of gives you an idea of the range that we can sample with this specific device. So this right here is a field map that we used while we were in the field to kind of document where we had been, where we were going. So this shows the extent of our sample range for this specific experiment. So as you can see, our most northern area is up here, right underneath the Albemarle Sound. Did part of the Outer Banks, come down through here, and then it gets cut off a little bit at the end here. But we go all the way down to the South Carolina border in the Sunset Beach area. And then this process took 2 weeks. It was the first 2 weeks of July 2024. So that is our sampling timeline as well as our sampling range. All right, I'm going to pray that this works because PowerPoint and video never seem to work how I want it to. So this is an actual video of our transect, one of our transects that we did in Swansboro, North Carolina, that did contain the light bulb tunicate that we were looking for. So I think this is going to work. So I'm going to pause it a little bit early just because I want to point this out right here. So this is actually one of the species themselves. So what we would do with these videos is we would get to our hotel room at the end of every day, and we would sit down and go frame by frame through these videos looking for these specific tunicates right here. And then we would write it down. Based on places that we did find it, we could create subsets of data for density within those sample sites. We also now have access to looking at all of these other species as well once we finish looking at this one. So very informative data, really cool process to get to do that. It's going to play again. All right, so getting to the GIS stuff. So this is a pretty baseline map here, but this is more just to show off where the museum data has the species located. So as mentioned before, it's native to this Caribbean area over in here. There's a large cluster in the Florida and eastern coast area of the United States now. That did not always used to be the case. And more importantly, over here in Europe, where it obviously had to traverse a lot of area to get there, there's a large cluster starting to appear over in this area near Italy, Israel, that area. So that is where the museum data currently shows that it is. Also, we'll point out the Bermuda area, which we'll talk about in a little bit. So our actual data that we generated, so this is a map of our presence-absence data for the specific species. So right here, the little star right there is where this species was originally reported during that original invasion back in 2014. And then the light blue dots are where we actually found the species when we did this sampling a few months ago. There's also one that got a little bit lost in the mix there for a total of 5 positive IDs. So as you can see, there are a couple here in this Beaufort Morehead City area, which is to be expected with that being the original place of invasion. And then down here, arguably more interesting, is in Swansboro. They were everywhere in Swansboro. So that is kind of the range that we were able to exemplify based on our data. And then obviously you see all these red dots are places that we sampled that did not contain the light bulb tunicate. So those go all the way up and down. So before I get into the predictive modeling, I just want to explain what Maxent is, because that's the primary technology that we use to make those maps. So Maxent is essentially ecological niche modeling, which can predict further distribution of a species based on different environmental factors associated with positive IDs and occurrences. And the more variables that you have, the more complex your models can get and the more accurate their predictions are going to be. And this is important because these models can be difficult to test if they don't have a lot of complexity, just because there's never enough data in the world to 100% accurately predict where something could go that isn't already there. So what this chart over here represents, so the dark blue dots on this longitude-latitude gradient demonstrate an observed individual species of whatever you want it to be. And then based on taking the actual occurrence itself and the environmental data that's associated with those occurrences, you can project where the true distribution of the species would actually be, which is represented by the light blue dots. So they're all clustered over here. But based on the parameters that these clusters were found in, you can see there's one up here, there's one down here. It can predict things to move in places you wouldn't necessarily expect it to. So yeah, that is essentially the quick rundown on Maxent. So this is our first Maxent map. So like the first one, this is more just to kind of show based on where everything was reported globally, where things are. So just for reference, the dark blue represents a 0% match for the specific habitat, and that goes all the way up to red, which meets all of the criteria for the species to live there. And just to reference, the environmental data that we use to generate this model were water pH, water temperature, salinity, as well as water velocity. Water velocity specifically helped a lot with this just because the species is subtidal, and so it eliminates a lot of places out in the deep ocean where it really wouldn't be feasible. So this is a bit zoomed in a little bit more. This has portion of Europe that I was talking about earlier, as well as this middle area with Bermuda, and then the eastern seaboard down here. So as you can see, a lot of these places that are lit up red in Europe do have occurrences of Clavolina oblonga. And then when we check here in a minute, that will also line up here. But it's interesting to see, based on our model, that all of these in Europe specifically are falling in these red areas, which means hypothetically it's working. This is the really interesting part, the part that we were specifically looking at. This is the east coast of the United States. And so as you can see, this really big cluster on the western side of Florida is all bright red, so that means it meets all of the criteria. And then as we go up the eastern coast, you can see they're all in that red to orange area right here, leading up to these pink dots right here, which is our specific IDs that we added to this museum data set. And then it kind of goes up through here and then tapers off once we start getting into middle of Virginia. So the main takeaways from what we have done with this research so far, so we have confirmed a spread in North Carolina from 2014. If indeed the invasion incident in Morehead City Beaufort area was the original identification of the species, and we mentioned earlier we saw it in Swansboro, so it's not necessarily moving north or south, but it definitely is moving. It also does not appear to be traveling quickly. Similar species have larvae in the water column for only around 3 hours, so it's really difficult for this species to move long distances on its own, especially in these calmer subtidal waters. And so likely it requires an external force to be able to move it instead of being able to move on its own. So this could be things like ballast shipping water, actual tunicate settlements on the bottom of docked ships that have been ported for a while, things of that nature. That's our leading theory at this point. And talking about climate change once again, so climate change may play a factor in this spread, but does not appear to be the primary catalyst for spread, so we would need to do further research to figure out how big of a role that plays. And then moving into further research, so salinity appeared to initially be more indicative of where the species would or would not be present. So a lot of the places that had higher salinities were the places that had positive IDs for this tunicate. So what we could do is do additional maxent models, weighting salinity compared to current occurrences. We also could just sample in different places that we obviously didn't get to because we only had 2 weeks to do this sampling. So those are future steps for salinity. And then in terms of expansion into Virginia, so if travel is restricted, we want to look at where in Virginia meets the criteria for a tunicate invasion. So if we go back a few, you can see there's nowhere explicitly bright red up in here except for maybe right here, which is actually in Norfolk, Virginia, which is a pretty big porting city in Virginia, so it'd be interesting to look up there. But there are places throughout here. It's a little bit more freshwater, but they do meet some of the criteria for a tunicate invasion. And so it would be interesting to go up there and check their docks with more funding to be able to figure out if it's already there, and if it's not there, which of the 3 criteria it meets and what their salinity levels are, just so we could gauge what the risk is for a future tunicate invasion up there. I just want to make a couple acknowledgments. This research would not be possible without funding from the Elon College Fellows Program, as well as the Elon Student Undergraduate Research Experience. And this all would not be possible without Dr. Ryan Kirk, who is a geographer at Elon University, who's the reason I'm standing here today. So shout out Dr. Kirk. I know you're not here, but thank you. Yeah.
This was really cool, thank you. So you mentioned like you guys think salinity is a big driving factor. Do you have any other, like off the top of your head, like contributing factors as to how why they're spreading? Like, I mean, I know we discussed like on boats and other things, but like, you know, do they have any natural predators or anything like that?
Yeah, so fun fact, most of the tunicates in North Carolina are invasive tunicates, but they've slowly worked their way into the ecosystems. So with this being a relatively new species, we don't have anything that eats fully grown light bulb tunicates. There are certain fish that will eat them when they're kind of in the bud period where they're still small. Once they're fully grown, at least to our knowledge, there isn't anything that eats them at this point. In terms of the salinity and different methods of spread, the only reason we say the boat would be pretty likely is because they could either settle or the larva could be in the ballast water and they can move somewhere shorter as opposed to like Bermuda, North Carolina. It's like Beaufort to Swansboro, and then they get dispersed that way. Part of the reason water velocity was so important is because obviously you need water velocity to move the larva, but these species also don't do well when they're settled in high, fast-moving water. And so it kind of creates a weird area where the natural reproduction doesn't work as well as it should. We also don't know enough about the natural reproduction habits of this species yet. The 3-hour larval period is from a different species of Clavalina that just is generally taxonomically similar. So we would need to do further research into the reproductive habits of the species as well. Yeah.
I'm not really familiar with the max int, so I was wondering if you could speak to that for a second and maybe explain why you picked that over any other interpolation. I mean, did you get like R, Python?
We did not. So my primary advisor, Dr. Amanda Chunko, has always been super into Maxent, and so when this project started going in that direction, she was like, "We're doing Maxent." So based on that, she kind of took the reins on that a lot more just because I was out in the field. But my understanding of it is essentially that every layer of environmental data that you add, it's almost like it's a polygon of some sort, to where it's like it goes from a 3-dimensional to a 4-dimensional figure and things like that. And so you can get really complex but really accurate predictions of where things are going to go. A lot of this is done with like smaller scale stuff, so doing it on a global scale was interesting to try and figure that out. It took quite a while. So yeah, I'm not sure if that exactly answers your question, but yeah.
Also related to Matt's end, you talked about putting in parameters for different environmental factors or layering those
Mhm.
environmental key environmental factors over each other to find hotspots. Was there any of those occurrences that were used as like training data, or you know what I mean? Like some algorithms take training data occurrence points into account to be like, okay, yes, these are the layers that Is that?
Yeah, no, that makes sense. I'm not 100% sure. Like I said, my advisor took a lot of that under her wing. To my understanding, the water velocity one took out a lot of like eligible areas, so that was an important layer that we added in later on. But yeah, salinity was also the other big one that we added in that seemed to eliminate a lot of the board and highlight other things. So like I said, not 100% sure if that answers your question. I'm still personally learning Maxent. We're not done with this research yet. So hoping to wrap that up in the next few months, but yeah.